Stanford University.
Okay, let's get started. All right, so welcome to lecture 14, and today we'll be talking about reinforcement learning. So some administrative details first. An update on grades. Midterm grades were released last night, so see Piazza for more information and statistics about that. And we also have A2 and milestone grades scheduled for later this week. Also about your projects, all teams must register your projects. So on Piazza we have a form posted, so you should go there, and this is required. Every team should go and fill out this form with information about your project that we'll use for final grading and the poster session. And the Tiny ImageNet evaluation server is also now online for those of you who are doing the Tiny ImageNet challenge. We also have a link to a course survey on Piazza that was released a few days ago, so please fill that out if you guys haven't already. We'd love to have your feedback and know how we can improve this class. Okay, so the topic of today, reinforcement learning. Right, so far we've talked about supervised learning, which is a type of problem where we have data X and then we have labels Y, and our goal is to learn a function that's mapping from X to Y. So for example, the classification problem that we've been working with. We also talked last lecture about unsupervised learning, which is the problem where we have just data and no labels, and our goal is to learn some underlying hidden structure of the data. So an example of this is the generative models that we talked about last lecture. And so today we're going to talk about a different kind of problem setup, the reinforcement learning problem. And so here we have an agent that can take actions in its environment, and it can receive rewards for its action. And its goal is going to be to learn how to take actions in a way that can maximize its reward. And so we'll talk about this in a lot more detail today. So the outline for today, we're going to first talk about the reinforcement learning problem. And then we'll talk about Markov decision processes, which is a formalism of the reinforcement learning problem. And then we'll talk about two major classes of RL algorithms, Q-learning and policy gradients. So in the reinforcement learning setup, what we have is we have an agent and we have an environment. And so the environment gives the agent a state. In turn, the agent is going to take an action, and then the environment is going to give back a reward, as well as this next state. And so this is going to keep going on in this loop on and on until the environment gives back a terminal state, which then ends the episode. So let's see some examples of this. First, we have here the cart pull problem, which is a classic problem that some of you may have seen in for example, 229 before. And so this objective here is that you want to balance a pole on top of a movable cart. Right, so the state that you have here is your current description of the system. So for example, angular speed of your pole, your position, and the horizontal velocity of your cart. And the actions that you can take are horizontal forces that you apply onto the cart, right? So you're basically trying to move this cart around to try and balance this pole on top of it. And the reward that you're getting from this environment is 1 at each time step if your pole is upright. So you basically want to keep this pole balanced for as long as you can. Okay, so here's another example of a classic RL problem. Here's robot locomotion. So we have here an example of a humanoid robot as well as an ant robot model. And our objective here is to make the robot move forward. And so the state that we have describing our system is the angle and the positions of all the joints of our robots. And then the actions that we can take are the torques applied onto these joints, right? And so these are trying to make the robot move forward, and then the reward that we get is our forward movement, as well as I think in the case of a humanoid, also you can have something like a reward of 1 for each time step that this robot is upright. So games are also a big class of problems that can be formulated with RL. So for example, here we have Atari games, which are a classic success of deep reinforcement learning. And so here the objective is to complete these games with the highest possible score, right? So your agent is basically a player that's trying to play these games. And the state that you have is going to be the raw pixels of the game state, right? So these are just the pixels on the screen that you would see as you're playing the game. And then the actions that you have are your game controls. So for example, in some games, maybe moving left, right, up, or down. And then the score that you have is your score increase or decrease at each time step. And your goal is going to be to maximize your total score over the course of the game. And finally, here we have another example of a game here. It's Go, which is something that was a huge achievement of deep reinforcement learning last year when DeepMind's AlphaGo beat Lee Sedol, which is one of the best Go players of the last few years. And this is actually in the news again. For some of you may have seen, there's another Go competition going on now with AlphaGo versus a top-ranked Go player. And so the objective here is to win the game. And our state is the position of all the pieces. The action is where to put the next piece down. And the reward is 1 if you win at the end of the game and 0 otherwise. And we'll also talk about this one in a little bit more detail later. Okay, so how can we mathematically formalize the RL problem, right? This loop that we talked about earlier of environments giving agents states and then agents taking actions. So a Markov decision process is the mathematical formulation of the RL problem. And an MDP satisfies the Markov property, which is that the current state completely characterizes the state of the world. And an MDP here is defined by a tuple of objects consisting of S, which is the set of possible states. We have A, our set of possible actions. We also have our R, our distribution of our reward, given a state-action pair. So it's a function mapping from state action to your reward. You also have P, which is a transition probability distribution over your next state that you're going to transition to given your state action pair. And then finally, we have a gamma, a discount factor, which is basically saying how much we value rewards coming up soon versus later on. So the way the Markov decision process works is that at our initial time step t equals 0, the environment is going to sample some initial state as 0 from the initial state distribution, P of S0. And then once it has that, then from time t equals 0 until it's done, we're going to iterate through this loop where the agent is going to select an action, A sub t. The environment is going to sample a reward from here, so a reward given your state and the action that you just took. It's also going to sample the next state, at time t plus 1, given your probability distribution. And then the agent is going to receive this, the reward as well as the next state. And then we're going to go through this process again and keep looping. Agent will select the next action, and so on until the episode is over. Okay, so now based on this, we can define a policy pi, which is a function from your states to your actions that specifies what action to take in each state. And this can be either deterministic or stochastic. And our objective now is going to be to find your optimal policy pi star that maximizes your cumulative discounted rewards. So we can see here we have our sum of future rewards, which can be also discounted by your discount factor. So let's look at an example of a simple MDP. And here we have grid world, which is this task where we have this grid of states. So you can be in any of these cells or cells of your grid, which are your states. And you can take actions from your states. And so these actions are going to be simple movements, moving to your right, to your left, up or down. And you're going to get a negative reward for each transition or each time step, basically, that happens, each state, each movement that you take. And this can be something like r equals -1. And so your objective is going to be to reach one of the terminal states, which are the gray states shown here, in the least number of actions, right? So the longer that you take to reach your terminal state, you're going to keep accumulating these negative rewards. Okay, so if you look at a random policy here, a random policy would consist of basically at any given state or cell that you're in, just sampling randomly which direction that you're going to move in next, right? So all of these have equal probability. On the other hand, an optimal policy that we would like to have is is basically taking the action, the direction that will move us closest to a terminal state. So you can see here, if we're right next to one of the terminal states, we should always move in the direction that gets us to this terminal state. And otherwise, if you're in one of these other states, you want to take the direction that will take you closest to one of these states. Okay, so now given this, this description of our MDP, what we want to do is we want to find our optimal policy pi star, right? Our policy that's maximizing the sum of the rewards. And so this optimal policy is going to tell us, given any state that we're in, what is the action that we should take in order to maximize the sum of the rewards that we'll get. And so one question is, how do we handle the randomness in the MDP, right? We have randomness in terms of our initial state that we're sampling, in terms of this transition probability distribution that will give us distribution over next states, and so on. Well, so what we'll do is we'll work then with maximizing our expected sum of the rewards. So formally, we can write our optimal policy pi star as maximizing this expected sum of future rewards over policies pi, where we have our initial state sampled from our state distribution. We have our actions sampled from our policy given the state. And then we have our next states sampled from our transition probability distributions. Okay, so before we talk about exactly how we're going to find this policy, let's first talk about a few definitions that's going to be helpful for us in doing so. So specifically, the value function and the Q-value function. So as we follow the policy, we're going to sample trajectories or paths, right? For every episode, we're going to have our initial state S0, A0, R0, S1, A1, R1, and so on. We're going to have this trajectory of states, actions, and rewards that we get. And so how good is a state that we're currently in? Well, the value function at any state S is the expected cumulative reward from following the policy from state S from here on out, right? So it's going to be expected value of our current of our expected cumulative reward starting from our current state. And then how good is a state action pair? So how good is taking action A in state S? And we've defined this using a Q-value function, which is the expected cumulative reward from taking action A in state S and then following the policy. Right, so then the optimal Q-value function that we can get is going to be Q star, which is the maximum expected cumulative reward that we can get from a given state action pair defined here. So now we're going to see one important thing in reinforcement learning, which is called the Bellman equation. So let's consider this Q-value function from the optimal policy Q star, which is then going to satisfy this Bellman equation, which is this identity shown here. And what this means is that given any state action pair S and A, the value of this pair is going to be the reward that you're going to get, R, plus the value of whatever state that you end up in. So let's say S prime. And since we know that we have the optimal policy, then we also know that we're going to play the best action that we can, right, at our state S prime. And so then the value at state S prime is just going to be the maximum over our actions A prime of Q star at S prime A prime. And so then we get this this identity here for our optimal Q value, right? And then also, as always, we have these this expectation here because we have randomness over what state that we're going to end up in. And then we can also infer from here that our optimal policy, right, is going to consist of taking the best action in any state as specified by Q star, right? Q star is going to tell us the maximum future reward that we can get from any of our actions, so we should just take a policy that's following this and just taking the action that's going to lead to best reward. Okay, so how can we solve for this optimal policy? So one way we can solve for this is something called a value iteration algorithm, where we're going to use this Bellman equation as an iterative update. Right, so at each step, we're going to refine our approximation of Q star by trying to enforce the Bellman equation. And so under some mathematical conditions, we also know that this sequence Qi of our Q functions is going to converge to our optimal Q star as I approaches infinity. And so this works well, but what's the problem with this? Well, an important problem is that this is not scalable, right? We have to compute Q of SA here for every state action pair in order to make our iterative updates, right? But then this is a problem if, for example, if we look at these, the state of, for example, an Atari game that we had earlier, it's going to be your screen of pixels. And this is a huge state space, and it's basically computationally infeasible to compute this for the entire state space. Okay, so what's the